Radical man. Remember when we talked about inverse operations, but then we didn't talk about the inverse operation of exponents? Well, that's because you weren't ready for it yet until now. Square root of x. Well, we square numbers to not double them, but multiply it by itself. The square root is the inverse of that. The equivalent statement is that if this is some number a, this is the same thing as saying that a squared equals x. You have to make sure of a certain thing. At least for Algebra 1, we do need to add a qualifier for x. X has to be a positive number. You can't take the square root of a negative number. It's not as bad as dividing by 0. You really can't do that. In a few years, you'll learn how to take the square root of a negative number, and that's fine. But in our context, it doesn't really make any sense. Let's try to see why this qualifier has to work. So, in order to square a number, we're squaring the number to equal 9. And that's cool. But what about negative 3 squared? Well, a negative times a negative is a positive, and that's still pretty cool. But you can clearly see, you might have already figured it out, the only result of squaring a number is that we get to a positive number. There's no number that when you square it, you'll get a negative number, because you need to do a positive number times a negative number to equal a negative number. We talked about this. Negative number. But that, by definition, needs to be two different numbers. So there's no way we can take a number and square it to equal a negative number. That's why we can't take the square root of a negative number. The question that the square root is asking is, what number squared equals this number? Along the same vein, say I did want to do the square root of 9. I want to find out what number squared equals 9. Well, 3 is an answer, but thinking about it for a little bit, wouldn't negative 3 also be an answer? That's kind of weird. Usually with algebra and these operations, we really only have one distinct answer. These two things are kind of equivalent, kind of to the statement up here. So let me put, isn't that weird that we have two different answers for the same question? That's what it is, right? Both of these numbers squared equal positive 9. So the shorthand that we have to say that it is not only two answers, but it's specifically the plus and minus 3, well, we just do that. That's what this shorthand is. I may have mentioned that before. If a number like 9 has a rational square root, 3, it is considered a perfect square. 16 over 49. We want to square root that whole thing. You'll see in a little bit that we just square root the top and then you square root the bottom separately. So that would become 4 over 7. And we'll do a plus and minus. 4 over 7. So that means that 16 over 49 is considered a perfect square. This is basically everything that's new. A new definition that you probably have heard of before, and a new vocab word. The rest of this chapter is just review with exponents, because radicals are exponents. But it doesn't look like an exponent, does it? It's got this weird little, I don't know, almost looks like a division problem, but with like a little hooky thingy right there. And like a little check. And then a hat. That doesn't look like an exponent. Yeah, in this form, the way that we write roots like this, it doesn't look like an exponent because it's just how we write roots. But you can take my word for it that the square root of x is the exact same thing as a fractional exponent. Get this into your head. Roots and exponents are the same thing. All of the laws that you just learned when it came to simplifying exponents and combining them and whatnot, they follow the same rules. What bewilders me is that you spend an entire unit learning about those exponent laws, and then they send you on a brand new adventure learning about the radicals and how they work. But as you'll see, they're the same laws. Because that looks different, because we usually use these, we have to reteach you all of those rules, but you don't. Let's say we want to do the cube root of something. So what we do is we do still a radical x, but kind of hanging out over here, we'll put the number in which we intend to do the root. And that's called the index. I don't expect you to memorize that. But this is the same thing as saying the cube root of x, which is the same thing as x to the 1/3, which is kind of like saying, okay, what number cubed is that number? So if I wanted to know 2 cubed is 8, then that's the same thing as saying I want the cube root of 8. What's that? Well, that's just 2. Now, notice here when I resolved the root, I didn't put plus or minus 2. That's because cube roots work differently, or odd numbered roots work differently than even numbered roots. An odd number root, you can have a negative number inside that, because -2 cubed like this is -8. So we better be able to take the cube root of -8, because that's a legitimate answer that we can get from cubing something. Up here, there's no way we can square something to get to a negative number. That's why we can't put negative numbers inside even exponential roots. We can't put negative numbers inside even numbered roots. But we can put negative numbers inside odd numbered roots. Just finish that up. And that's just because, remember when we learned exponents from before, we have that odd one out that makes the whole thing negative again. So like -2 times -2 times -2. These two 2's would make it +4. But then we have that odd one out. So no matter how many of them we're multiplying together, if there's an odd number of negative numbers, that odd one out is going to just make the whole thing negative again. So in general, we would write a root. So we got the nth root of x is the same thing as raising x to the 1/n. And you can take all of your exponent rules from before, apply them to the inverse operation of exponents, and you're good to go.